In this video, we are going to solve a problem involving a combined heat transfer. Here's our problem. A flat plate solar collector is mounted on a building's roof. The inner and outside surfaces of the glass cover are measured to be 32 degrees Celsius and 28 degrees Celsius respectively. The glass cover has a surface area of 4 square meters, a thickness of 0.5 centimeters, and a thermal conductivity of 0.5 watts per meter degree Celsius. With a convection heat transfer coefficient of 9.5 watts per square meters degree Celsius and an ambient temperature of 18 degrees Celsius, heat is lost from the outside surface of the cover through convection and radiation. Calculate the fraction of heat lost by radiation through the glass cover. So listing all the given, we have inner temperature is equal to 32 degrees Celsius. The outside temperature is 28 degrees Celsius. The area of the glass is 4 square meters. A thickness of 0.5 centimeters. Our thermal conductivity is equal to 0.5 watts per meter degree Celsius. The convection heat transfer coefficient is 9.5 watts per square meters degree Celsius. And we have the ambient temperature, which is equal to 18 degrees Celsius. So what are we going to calculate in this problem? Is the fraction of heat lost covered by radiation. Fraction of heat lost is given by the equation F equals Q rad over Q dot conduction, where Q dot rad is the rate of radiation heat transfer and Q dot conduction is the rate of conduction heat transfer. So in order to find the value of the fraction of heat lost, we will first need to find the values of the rate of radiation and conduction heat transfer. So solve for the rate of conduction heat transfer and rate of radiation heat transfer. Rate of conduction heat transfer is given by the equation K. Q dot conduction is equal to K times A times delta T over L, where K is the thermal conductivity, A is the area, delta T is the change in temperature, and L is the thickness. So looking at our given, we have the values for the thermal conductivity, the area, as well as the temperatures. So since we all have the given, we will just plug in this into our equation, and we will get Q dot conduction is equal to the thermal conductivity, which is 0.5 watts per meters degree Celsius, times the area, which is 4 square meters, times the change in temperature is equal to inner temperature minus outside temperature, which is equal to 32 degrees Celsius minus 28 degrees Celsius, over the thickness, which is 0.5 centimeters, which is equal to 0.005 in meters. So calculating, we will get Q dot conduction is equal to 1600 watts, and this will be our rate of conduction heat transfer. Now that we have the value of our rate of conduction heat transfer, we will now solve for the rate of radiation heat transfer. Rate of radiation heat transfer can be calculated using this equation. Q dot rad equals Q dot conduction minus Q dot convection. So since we already have the value of our rate of conduction heat transfer, which is 1600 watts, we will just solve for the rate of convection heat transfer. So rate of convection heat transfer is given by the equation Q dot convection is equal to H times A times delta T, where H is the rate, where H is the convection heat transfer coefficient, A is the area, and delta T is the change in temperature. So plugging in all our given values, we'll get 9.5 watts per square meters degree Celsius, times the area, which is 4 square meters, times the change in temperature is equal to the outside temperature minus the ambient temperature. So we will get 28 degrees Celsius minus 18 degrees Celsius. Calculating, we will get Q dot convection is equal to 380 watts. Now that we have the values of both rate of conduction and convection heat transfer, we will just plug in this into our equation. Q dot rad is equal to the rate of conduction heat transfer, which is 1600 watts, minus the rate of convection heat transfer, which is 380 watts, and we will get 1220 watts, and this will be the rate of radiation heat transfer. So since we have the values of our rate of conduction and radiation heat transfer, we can just plug in this in our equation, in this equation. So plugging into our equation, we'll get F equals Q dot rad over Q dot conduction is equal to 1220 watts over 1600 watts. When calculating, you'll get F equals 0.7625 or 76.25%. And this will be our final answer in this problem.